All right, so in addition to the distillation lab we did, and we want to use gas chromatography to analyze the distillate that we collected during that lab. So for this particular discussion, we will take a look at what is GC, what are the basic components of the GC, and then how do we analyze the sample. And we will also demonstrate how to use the Trace 1300 GC by Thermo Scientific. So this is a schematic diagram of gas chromatography. Basically, for any chromatography instrument that we have here, gas chromatography instrument that we have here, we got to have carrier gas. So carrier gas that we're using nitrogen gas. We can use helium, we can use nitrogen, all those inert gases here. Okay? And then we have a column. And the column is being used to separate the possible components in a mixture here. So what we do here is that we have an injector on the column, and we can inject the sample into the column. We also put that column in a heated environment we call oven. Okay? So this oven will actually keep the sample in there pretty hot. And remember, it's the term GC in gas chromatography. We have to vaporize pretty much all the samples we're trying to analyze here. So what we have here is once the sample is getting into the column, once you inject the sample into the column there, carrier gas is going to blow through the column. Okay? So in this case, you have a liquid sample, you put it into the sample, into the column there, and things start vaporizing. And things that has a lower boiling point will actually vaporize first. And then things with a higher boiling point will vaporize at a later time. And due to that small difference, as you have carrier gas blowing through the column there, and that small difference will add up. And if you have a column long enough, eventually, for different components with different boiling points, once you put them in the column there, as they travel through the column, eventually they will be able to separate. So the lower boiling point component will come out first and passing through something that we call a detector, and then we will have a data system where we can display the peak that appears. And we call them once the sample comes out, and using the detector there, we can actually catch who comes out first, at what time, and what is the intensity of the peak. Okay, so looking at the column there, and the basic structure of the capillary column there, and we have multiple layers there. Okay, in here we have a polyimide coating, and just to protect, and then we have fused silicone there. Stationary phase with the engineered self-cross-linking technology, and that is what's inside the column there. So you can see, and it's all coiled up. It's a fairly thin column there, and with the blown up here, and you can actually see a lot of detail about the column there. And these columns are actually very thin, very small in terms of the diameter, and we can have a 20 feet, 30 feet long column coiled up, and then from there, once you put the sample in there, and the sample will travel the entire length of the column there, resulting in a separation. Okay. So for the injector, when you put the sample into the column there, there is a split and splitless injector there, and depending on the sample you're trying to analyze there. So the carrier gas is hooked to the injector, and then once you have the sample in the syringe, you push it in there, and then only a very small amount of sample will get into the column. And once you put the sample into the column, and carrier gas will carry the sample through the column until it comes out from the other end of the column there. And then on the other end, we have our detectors. Right? So here, the common detectors that we use to identify the sample, we have a flame ionization detector, we call it FID, and we also have a thermal conductivity detector, electron capture detector, flame photometric detector, and photoionization detector. And so here in our laboratory there, and the one that we're using a thermal conductivity detector. We also have a flame ionization detector attached to the in this instrument there. Now, in order to use flame ionization detector, you actually have to have, according to the name, you actually have to have a live flame. And how do we get the flame there? We burn hydrogen gas. So sometimes in the GC lab, you see multiple cylinders. One of them is hydrogen gas, and then burning nitrogen gas in the presence of oxygen, well, you have that flame there. When the sample passes through, well, the combustion of the sample will cause a signal change, and then you can detect the sample. And thermal conductivity by similar mechanism there. When you have a sample coming out, and then that will actually alter the conductivity of the circuits there, and from there that will trigger a signal where you can use the data system that you can display the signal there in the form of a peak in the GC there. Okay, so talking about the chromatogram, this is a sample chromatogram based on this particular experiment. So what we see here is that here we ask you to collect the distillate below 82 degrees Celsius. Now remember, cyclohexane has a boiling point of 81 degrees Celsius. So anything below 82 degrees Celsius, it should be the lower boiling point component from the distillation part of the lab there. And here you see two different peaks there. We can identify the peak based on a standard that we run. We can have pure cyclohexane injected in the sample and let it running through, and then we will know what time, based on the retention time, what time does the cyclohexane comes out, and then what time does the methylbenzene comes out. And then when you run the sample here, and the instrument will be able to tell when the first peak comes out, it should be your cyclohexane. When the second peak comes out, that should be your methylbenzene. So what we're looking for really is that we are looking for the relative area in percentage underneath each peak. So back in the old days, and it's fairly, without the computer to do the integration for us, it's fairly difficult to figure out the area underneath the absorption, underneath each peak here. But now with the computer there, we can easily do that. So this really is the column that we should be focusing on. So the relative area in terms of percentage underneath each peak. So we will be looking at this particular column there, and we know the first component that is below 82 degrees. The majority of that distillate should be cyclohexane. Now, if you look at the percentage here, we got 57.28% of cyclohexane. Yet we still have 42.72% as methylbenzene. So it is still a mixture, but we do have a simple majority as cyclohexane, the lower boiling point component that comes out first. So, and then there's another chromatogram and showing this is the simple distillation, but it's above 82 degrees Celsius. Now, according to what we talked about in Lab 5 when we're doing the distillation there, and anything above 82 degrees Celsius, well, the majority of that distillate should be the higher boiling point component. Well, take a look at this column again. We have 28% of cyclohexane, and we have 72% of methylbenzene. So in this case, once again, we're looking at the relative area in percentage underneath each peak. We can tell the above 82 degrees Celsius, the majority of the component of that sample is methylbenzene, the higher boiling point component. And we also want you to compare between simple distillation and fractional distillation. Which one provides a better separation? Well, let's take a look at the chromatogram from a fractional distillation below 82 degrees Celsius. So here, once again, we will be focusing on the relative area in percentage underneath each peak. So the fractional distillation below 82 degrees Celsius, and when you look at the numbers here, cyclohexane is 70%, 69.05%. Compared to the simple distillation, the first slide of the chromatogram, compared to the simple distillation, 57%. Well, there is quite a bit of an increase in terms of the percentage of the cyclohexane there. So in this case, we can conclude that fractional distillation is providing a better separation because you have a higher percentage of a lower boiling point components in the distillate that you collected below 82 degrees Celsius. And we can also do a comparison for the above 82 degrees Celsius, chromatogram between the fractional distillation and simple distillation. So simple distillation, fractional distillation, you can see here, at a higher temperature, you're supposed to have a higher component, a higher percentage of the higher boiling point component here. Now we have 76.30%. Compared to the simple distillation, that is a higher percentage in terms of methylbenzene. Therefore, we can conclude, based on the chromatogram that we have here, we can conclude that fractional distillation is more effective compared to the simple distillation when we do the separation, when we go through the distillation process. And with that, we will take a look at the instrument itself and quickly do a quick demonstration, and then we will have you upload your sample to the automatic sampler, and then we will run the chromatogram of your sample. This is our thermo-scientific trace gas chromatography and trace 1300, and it's a very useful analytical instrument. And again, we want to give you a quick look at the basic anatomy of the instruments here. So this is the instrumental panel here, where you can set up all the parameters that you need to run your sample. This is the auto sampler. Okay, you can load up to 160, 180 different vials in here. So back in the old days when we do GC, when we do sample analysis, sometimes the technician needs to do one sample at a time. With the help of the auto sampler, all we need to do is to put the sample in there, set the program, and then click on go. And next morning you come back here, everything is done. So auto sampler is definitely a very useful part of the instrument for analytical labs there. Okay, so if you look at the oven here, well, this is the oven, the heated environment there, and you can see that column that we were talking about. Okay, so with that column coiled up in there, the sample is being injected. And for this particular instrument, we have multiple detectors there. We have a thermal conductivity detector. We also have a flame ionization detector. So the injection port, we have multiple injection ports. And then with the auto sampler also has an injection port for itself. Right? So, and here you see the display. And then again, the software is controlling the instrument there. In order to do the analysis here, we have, for the demonstration purpose there, we have 6 different vials loaded on the auto sampler. Okay? And then we will set up a new sequence so that this computer will tell the instrument when to pick up the sample and to run the analysis. Okay? So once you open the software there again, and you can click on create, and then create a new sequence, okay? And select the new sequence there. We'll ask you which instrument do you want. One computer can actually control multiple instruments there, but in this case, we have a dedicated computer for this particular instrument. So we will just do next, okay? And it will ask you, do you want to do a manual injection or do you want to use a sampler? Well, with the auto sampler, why do we want to use a manual injection, right? So we select the sampler and click on OK. And here we got 6 vials on there, and you have to identify the position of each of the vial there. So you start the vial, total number of vials 6, and you start position as number 1, and then you do 1 injection per vial. Okay? And then we go to the next, and the sequence you have to, when you create a new sequence there, you have to select a methodology. Now, the methodology was as developed by the chemist, and so we put them in the instrument there. And when you run your sample, you don't really need to create your new methodology. It's already in there. Okay? So we will select that, and then you will be able to name the name your run here. So we can call it a test run. Okay? So in this case, once we have that, we'll finish it, and then the objective name there, we can put our name in there. So we say we'll do test run -1 and July 29th, 2020. So we can save it. Okay. Now the sequence is ready, and you're ready to click on the start. The instrument will start. Will start a run. Okay, let's do that quickly. This is the start button there. And the signal is being sent to the instrument from the computer. And then within a couple of minutes, you will see the action of the auto sampler. And robotic arm will pick up the sample and then use a needle to actually poke into the sample, take some sample out, and then it will inject into the column there. And then each run takes about 7 to 8 minutes, right? So we're not going to watch all 6 runs there, and we'll just have you take a look at the first sample there, and then from there, once we have the first sample, we will display the chromatogram, and we can print it out, or we can save it on the flash drive. So we'll just give it a couple of minutes there. And you can see the sampler, auto sampler, start moving there. And again, it needs to locate itself and the first vial that we put in there and in the position number 1. And the needle is going in there, picking up the first sample. And we always need to rinse the needle a couple of times. So you see the robotic arm going back and forth and taking some more sample from the vial, dump it into the, after the rings, and dump it into a waste container. And they will do that a couple of times before it actually do the injection. Okay. Now the sample is being drawn into the needle and ready for the injection. And these are the injection ports. And we have a designated injection port for the auto sampler. Sample being injected, and the run starts. Okay. And again, it takes about 7 minutes for the chromatogram to finish, for the samples to go through the column there. Once they come out from the column there, we will be able to see a display on the screen for the chromatogram. Want to pause it for a while, and then once the voice is recorded. All right, so the run is finished, and now you see the chromatogram being displayed on the computer screen here. So this is obviously, when you look at the size of the peak here, the cyclohexane is much smaller compared to the methylbenzene peak there. So if you look at the relative area, it indicates that 22% of this particular sample is cyclohexane. The other 77.93%, 78% is methylbenzene. So from there we can say this is most likely from a fractional distillation process, and it is the distillate that is above 82 degrees Celsius, and the majority is a higher boiling point component, methylbenzene, and then there is a still smaller amount of the cyclohexane there, or the lower boiling point component. So here we can save this particular file to a thumb drive, or we can print it out, and then that's pretty much what we need to do. And again, for this particular experiment, each person, you will end up with 4 chromatograms, 2 for the simple distillation, 2 for the fractional distillation, and then for each of the distillation there, 1 below 82, the other above 82. So total 4 chromatograms. And your job when you write the lab report is to analyze all the 4 chromatograms and trying to figure out which distillation method is more effective, and then based on the percentage number, that conclusion can be easily drawn. So enjoy doing the analysis there, and I hope to see you in the next lab.